Hey students, this is a lecture on graphing vector equations. Okay, so vector equations are equations that have a function which has an input of t and the output is a vector, and the vector is a function of t. And here we're just going to be learning how to sketch graphs of them. And if you're in my class, the graphs that you do are multiple choice, so you just have to choose the correct picture. Okay, so example. Determine the graph corresponding to the given vector equation. In other words, sketch a graph of each vector equation. Okay, and for our first example, our vector equation is r of t. Okay, so it's a vector that's a function of t, and this equals 2ti, so 2ti plus 4 minus 2tj. Okay, and they say that the parameter t goes from 0 to 2. Okay, so t is greater than or equal to 0 and less than or equal to 2. All right, so you're going to notice something here. It's a two-dimensional vector equation, but we are going to be graphing these in 3D, so with 3 dimensions. It's just there's no k hat here, so there's no third component. So this is just going to be two-dimensional. So we want to sketch a graph of this vector equation, and they tell us that t starts at 0 and t ends at 2. Now probably the easiest way to do this is by plotting points, okay? And when you're plotting points, you can also calculate the derivative to determine the velocity if you want to. But you don't have to take the derivative if you don't want to. You can just plot points and get a pretty nice graph from plotting points. Okay, so the plan is to plot points for different values of t. For different values of t. And remember, t is often representing time in physics or other applications, and t is also called the parameter. And we're plotting points for different values of t. Okay, so what we're going to do is we're actually going to plug in t equals 0, plot that point, plug in t equals 1, plot a point for that one, and plug in t equals 2. And we're going to plot those 3 points, and then we're going to go ahead and draw a smooth curve passing through those points. And because it's a vector equation, that curve actually has a direction. And we're going to be doing this in 3D, okay? In 3D. So even though this equation that they gave us doesn't have a third component, it doesn't have a k, we're still going to be plotting them in 3D. Okay, so what we're going to do here is we're going to start with t equals 0. Okay, so when t equals 0, what do we have? Well, we plug in 0 into r of t. So we're going to have r of 0 equals 2 times 0, I, plus 4 minus 2 times 0, j. And then there's no k component, so there's no third component. Okay, and then if we simplify this, obviously we have 2 times 0 is 0. So here we just have 0i plus 4 minus 2 times 0 is 4j. And then even though we don't have a k component, I'm going to go ahead and write plus 0k. And the reason I'm doing all of that is so that we can plot this vector as a point. So we found the vector that this equation gives us at t equals 0. And now we can go ahead and graph this vector as a point. Okay, so in 3D, remember that the x-axis is the one that comes out at you. And then the y-axis is usually the horizontal axis. And then the z-axis is actually the vertical axis. Okay, and I'm going to probably zoom in on that so that we can get a better picture. So what we're doing is we're going to plot 0, 4, 0. It's actually a vector, 0, 4, 0. So x is 0, y is 4, and z is 0. Remember, they're of the form x, y, z. All right. So if I zoom into my graph, both x and z are going to be 0, but y is going to be 4. So on the y-axis, we're going to go out to 4. So let me kind of zoom in on this. So 1, 2, 3, 4. On the y-axis, we're starting right here. And remember, x and z are 0, so that's why we're on the y-axis. Because z is right there, and x is right there, but y is 4. Okay, and that's our first point. That's where t equals 0. And if you wanted to, you could draw that as a vector, but that isn't actually as useful as just plotting a point. Okay, plotting a point is more helpful there. And you'll see why in a minute. Because what we're trying to do is we're trying to draw a curve that's traced out by these vectors. And so really we want to just plot points and then draw a smooth curve through them. But the direction of the curve is important because it's vectors. Okay, and vectors have a direction. All right, so that's our first point where t equals 0. And then for our second point, we're going to go ahead and do t equals 1. So once again, we're going to be plugging into our equation r of t. So now we're going to do r of 1. Okay, so when t equals 1, we're finding r of 1. Okay, and r of 1 is going to be 2i plus 4 minus 2 is going to be 2j plus 0k. Okay, so plugging in here, plugging in 1, we get 2i plus 2j. 2i plus 2j. And then, of course, because k is not there, we have 0k. But I'm going to go ahead and write 0 so that we can plot that point. All right, so our next point that we're plotting here is going to be 2, 2, 0. So if I zoom back into my figure, into my graph, we're going to graph x is 2, y is 2, and z is 0. Okay, so x is 2, x is 2, y is 2, and z is 0. So that point is going to be right about here. Okay? And then just to get a better graph, we're going to graph one more point after this. So we did t equals 0, we did t equals 1, and now we're going to do t equals 2. So t goes from 0 to 2, and it just seemed easy to me to choose 0, 1, and 2 as our different values for t, for plotting points. Okay? So now we're going to do t equals 2. So when t equals 2, we're doing r of 2. So plugging into the original vector equation, we're going to get 2 times 2 is 4i, plus 4 minus 4 is 0j, and then of course once again we have plus 0k. So we're going to have 4i plus 0j plus 0k. For I plus 0j plus 0k. So as a point, that is 4, 0, 0. And we'll talk about the direction, because obviously vectors have a direction, so it makes sense that a vector equation would have a direction. But first of all, we just want to plot these points. So this next point, x is 4, y is 0, and z is 0. 4, 0, 0. So for 4, 0, 0, this is 4 on the x-axis, and then y and z are 0, so we're right here. And if I were a true artist, you would be able to tell that this is actually a straight line. And it is supposed to be a straight line. Now this one is going to be a straight line, and how do I know that? Well, if I connect the dots, it should look like a straight line. And I wasn't an artist, but I was close enough that I can make it believable. Now, how do I know that this particular vector equation is a straight line? Well, looking at the original equation, we didn't have any powers, we didn't have any square roots, we didn't have any exponential functions or anything. So this is what's called a linear vector equation, because it has no powers. So let me zoom out a bit here so I can write that over here. This is a linear vector equation. Okay, so this one has no powers. No powers, radicals, etc. So it just has t. It's just a function of t, but it doesn't have anything else going on, so it's linear. And because it's linear, the word linear means that the shape is going to be a line. Okay, so that's how I knew it was going to be a line, is just by looking at it. And another way you can do that is you can take the derivative. If you take the derivative of this vector equation, you're going to get only constants. And if you get constants as the derivative, that also means it's linear. Okay, because the derivative of 2t is 2, and the derivative of 4 minus 2t is negative 2. So you would have 2i minus 2j plus 0k. That's a constant. The derivative is a constant. So that's another way you would know that it's linear. Okay, but linear, again, the graph is going to be a line. So if I zoom back into my picture here, we can see that we have a line. Now the only question is, because it's a vector equation, which direction is the line going? Well, fortunately, we remember where we started the graph. Okay, so the graph started here at t equals 0. We were right there. And then at t equals 1, we were right here. And then finally, at t equals 2, we ended on the x-axis. So that was right here. Well, remember that the direction of a vector is important. And so the direction of a vector equation is not just a curve, but it also has to have a direction. And the way you indicate the direction is with an arrow. Well, because it started at t equals 0 right here, and we can see over time as t increases, the graph is moving this way, we need to draw an arrow going in the direction of the flow. Okay, so we draw an arrow on our graph to show that it's going this way. Let me erase that. Okay, and one arrow is enough. You could draw more than one arrow, but we can see from the picture the arrow is pointing this way. So if someone looks at our graph, they know, oh, hey, it's going this way. And again, the way we know the direction of the arrow is just because we knew where the graph started and we knew where it ended. So we know that as the parameter t increases, we're going along this line. Okay? So there's our graph. And that's our first example. Okay, now not every equation, of course, is going to be linear. We also have other shapes. So for our second example, we'll look at a nonlinear vector equation. So for example number 2, let's look at a nonlinear vector equation. So this one is r of t equals, let me open this up. Sorry, I closed my notes for a moment. R of t equals 8 cosine of t times I plus 8 sine of t times j. Okay, and t, the parameter t, goes from 0 to 2 pi. Okay, so they tell us that t is greater than or equal to 0 and less than or equal to 2 pi. Now, right off the bat, when you look at this, you should notice that it is not linear. How do I know it's not linear? Well, we don't just have t here, we have a trig function. We have cosine of t and we have sine of t. So this is nonlinear. This is nonlinear. To be linear, your power has to be 1, and you can't have any other stuff. You can't have any trig functions, you can't have any powers or exponents or radicals or even any fractions like that. Okay, so this is nonlinear. So you might be wondering, well, how do you graph a nonlinear vector equation? Well, to graph a nonlinear vector equation, you're going to want to, once again, plot points, but you have to be a little bit more careful about the shape of it, because the shape isn't just going to be a line. Okay? Shape is not just a line. Okay? Nonlinear means non-line, so the shape is not a line. All right, so how do you graph it? Well, once again, you can plot points, but you just need to be careful to get the correct shape there as you plot the points. So for example, on my math lab, they actually plot points just the way we did, and they do 0, which is where t starts, okay? And then they do 2 pi. And they also calculate the velocity and the location. So they take the derivative, which is interesting. That might be helpful. If you want to take the derivative, you can. Okay? but we're going to do 0, pi, and 2 pi. Since we start at 0, halfway is at pi, and then we end at 2 pi. Okay, so let's start. We're still going to plot points. Still going to plot points. But this time we're going to do t equals 0 for our first point, and then pi, and then 2 pi. So let's start with r of 0 for t equals 0. So when t equals 0, we get r of 0 is going to be 8 times cosine of 0 I plus 8 times sine of 0 j. Eight times cosine of 0, oops, yeah, 8 times cosine of 0 I plus 8 times sine of 0 j. Okay, and once again, these are in 3D, so because they aren't giving us a k, we're going to go ahead and write a 0k as the third component. Okay, so plus 0k. Okay. Well, look, it says okay, and I said okay, so there's some kind of pattern there. Okay, 0k. And then, so what's cosine of 0? Recall that on the unit circle, cosine is the x-coordinate, so cosine of 0 is actually 1. Okay, so we have 8 times 1 times I plus sine of 0 is 0. So we have plus 8 times 0 j plus 0k. So really what we have here is 8i plus 0j plus 0k. Okay, so if we plot that as a point, it's actually a vector, but we're just going to plot it as a point. It's 8, 0, 0. Okay, and I'm going to try to have my picture be a little bit bigger this time so I don't have to keep zooming in. So let's see how that goes for me. Okay, so our horizontal axis is our y-axis. And then the axis kind of coming out at us is the x-axis. And then the vertical axis is, of course, our favorite one, and that is the z-axis. At least it's my favorite one. Especially on these problems, because the z is always 0, which makes it a lot easier than the other ones. Okay, so there I have my axes. And we're starting at x is 8, y is 0, and z is 0. So we're going to be on the positive x-axis here. And we're going all the way out to 8. Okay, but because y and z are 0, we're just on the positive x-axis. Okay, and then we're going to go ahead and plot a couple more points. So for our next point, let's do t equals pi. Okay, so over here, when t equals pi, we're going to be doing r of pi. Okay, r of pi. So our function r was 8 times cosine of t I plus 8 sine of t j. So now we're going to have 8 times cosine of pi I times cosine of pi I plus 8 times sine of pi j, okay, plus 8 times sine of pi j plus, once again, our k component, because they're not writing anything, is 0. So plus 0k. Okay, so we have 8 cosine of pi I plus 8 sine of pi j plus 0 times k. All right, and recall that cosine of pi is actually the same as -1. Okay? Oops. So we have 8 times -1 times I plus sine of pi is 0. So we have 8 times 0 times j plus 0k. Okay, so we have -8i plus 0j plus 0k. Okay, so as a point, that's -8, 0, 0. So let's go ahead and graph this point. X is -8, y is 0, and z is 0. Okay, so if this is 8 here, then -8 would be down here, back there on the x-axis. Okay, and I'm going to go ahead and label this. So this first point was where t equals 0. And then the second point over here is where t equals pi. Okay? And then we're going to do one more point for now, which is t equals 2 pi. Okay? T equals 2 pi. Okay, so for t equals 2 pi, what do we get? Well, if we plug in 2 pi into our vector equation, we get r of 2 pi equals 8 times cosine of 2 pi, 8 times cosine of 2 pi I, plus 8 times sine of 2 pi j, 8 times sine of 2 pi j. And then, of course, we don't have a third component, so we're going to go ahead and write plus 0k. Now, if you remember, 2 pi is the same as 0 when it comes to the unit circle and trig functions. So cosine of 2 pi is actually 1. Okay, so here we have 8 times 1 is 8i. Sine of 2 pi is 0, so we have plus 0j plus 0k. Okay, so that's the point 8, 0, 0. And this is actually the point that we started with, which is interesting. So 8, 0, 0. So what have we done? We've gone from at t equals 0, we went here. And then at t equals pi, we went all the way to the negative x-axis. And then now we're back where we started. Okay, so what kind of shape is this going to be? So at t equals 2 pi, we're actually right back where we started. Well, some of you might have noticed something about this graph, which is cosine and sine are actually the x and the y coordinates of the unit circle. Now, this is not a unit circle. This is going to be a circle of radius 8 because each of these is multiplied by 8. Okay, so how do I know that it's a circle of radius 8? Well, once again, remember that cosine is actually the x coordinate on the unit circle, and sine is the y-coordinate on the unit circle. So this here is actually going to be a circle of radius 8. Okay, a circle of radius 8. Which should make sense to you when you have trig functions like that. They're the exact trig functions that you would have with the unit circle. It's just because they're multiplied by 8, it's going to be a circle of radius 8. So then the only question is, how do we sketch the rest of the circle? Well, I'm not much of an artist, so I'm just going to give it my best shot. But this is supposed to be a circle. So here I go, for better or for worse. It's not going to exactly look like a circle, first of all, because I'm not an artist, and second of all, because it needs to look a little bit different from a circle since it's actually in the XY plane. Okay, so it's going to look something like that, because it's not facing us directly, it's a circle in the XY plane. But because it's a circle, we know that on the y-axis, we know that it's going through -8 and 8. And then the question is, which direction is this circle going? You might be wondering, well, where do we even put our arrow for this circle? So in other words, does the arrow go this way or does it go that way? Now there's a couple ways you can do this. One way is you can take the derivative. That's what they do on my math lab. Another way of doing it would be you could actually just plot another point. Like for example, we could plot t equals pi over 2. So if you don't want to take the derivative, you don't have to. You can actually just plot another point. So we can plot t equals pi over 2. And if t equals pi over 2 is right here, we know we're going to be going this direction. Whereas if t equals pi over 2 is here, we know we're going to go that direction. And I'm getting the feeling like some of you are probably expecting it to be right here, and you're going to be correct. Okay, because of the way the unit circle works, so a circle of radius 8 works the same way. So we're going to plot one more point. Plot one more point. Or you can alternately take the derivative at one of those points. But I don't feel that taking the derivative is really necessary. So it's probably easier to just plot one more easy point. So I'm going to plot one more point. So I'm going to do t equals pi over 2. So when t equals pi over 2, we have r of pi over 2 okay, so that's going to be 8 times cosine of pi over 2 I plus 8 times sine of pi over 2 j plus 0k. Okay, and we know that, well, hopefully we remember from our unit circle that cosine of pi over 2 is the same as the x-coordinate at 90 degrees, so when we're on the positive y-axis. And so that's going to be 0. Okay, so we're actually going to get 0i, and then sine of pi over 2 is 1. So we're going to have 0i plus 8 times 1 is 8j plus 0k. So if we plot this point, 0, 8, 0, this is going to tell us where we are in our graph when t equals pi over 2. And that way we'll be able to see which direction we're going. whether we're going clockwise or counterclockwise. Okay, so once again, our point is 0, 8, 0. And that's where t equals pi over 2. And that's exactly where I expected it to be. And hopefully that makes sense to you because of the way the unit circle works. So 0, 8, 0 is right here on the positive y-axis. And that's where we are in our vector graph when t equals pi over 2. Okay, and then without bothering to take up more time of your time on it, I wanted to point out that if t equals 3 pi over 2, and you look over here, you're going to find that your next point would be right there. So if you wanted to graph another point, that would be t equals 3 pi over 2. Okay, but we don't really need to do that because we can see which direction this is flowing. So we start it here, right here, at t equals 0, and then at t equals pi over 2, we're right there. At t equals pi, we've moved to here. At t equals 3 pi over 2, we're back there, and then at t equals 2 pi, we're back at t equals 0. Same place. So we're right back here on the positive x-axis. So once we do an entire circle like that, it's clear that the direction of the circle has to be this way. Okay, we can see which direction the circle is moving. All right, and then if you wanted to do the derivative, you would see that the derivative going along here would tell you the velocity. Okay? All right, so we have a circle here on the xy plane, and that's not too bad of a drawing as far as my drawings go. Could be worse. Okay, so what I want to do is one more example of graphing a vector equation. So for this next one, we're actually going to be doing another nonlinear equation. Okay, so for example number 3, we're going to graph the nonlinear equation r of t equals the quantity t squared minus 4 times j plus 4t times k. Okay, so r of t equals the quantity t squared minus 4 times j plus 4t k. All right, and they tell us that t goes from -2 to +2. So first of all, you should notice that this equation is nonlinear because we have a power here. So this is going to be nonlinear, and it's t squared. T squared minus 4 is nonlinear. Okay, and then the question is, what kind of shape is it going to have? Well, you can plot points, and that'll be fine. But the only thing is, what kind of shape do you think it's going to have? Well, this is a parabola. T squared minus 4 as our j component is a parabola. How do I know it's a parabola right away? Well, the highest power is 2. We don't have any trig functions. So this power of 2 is generally a setup for a parabola. Okay, but we can still plot points. It's just important that we know the basic shape. And you also notice something else about this equation. We don't have a first component. So we don't have any i's here. We have a j and we have a k. So we have a y and a z, but we don't have an x. Okay, so let's plot some points. starting with t equals -2. Okay, when t equals -2, plugging into this function, we get r of -2 equals -2 squared, which is 4, minus 4 is 0j. And don't forget I, because they didn't write it, we have a 0i as well. So we have 0i plus 0j minus 8k. And I got the minus 8k because -2 times 4 is -8. Okay, so we have 0, 0, -8. And that's going to be our first point. That's where t equals -2, which is where our graph is going to start. Okay, so if we go ahead and do a sketch of this, our horizontal axis is our y-axis. The axis coming out at us is our x-axis. And then our vertical axis is, of course, our z-axis. Our first point that we're going to plot when t equals -2 is 0, 0, -8. So x is 0, y is 0, and z is -8. So we're going to start here at -8 on the z-axis. This is where t equals -2. Okay, and I have a rough idea that it's going to be a parabola, but I'm still going to have to do at least 2 more points to figure out where to draw this parabola. Okay, so let's do t equals 0. Since we're starting at -2 and we're ending at +2, halfway is going to be at t equals 0. So for our next point, we're going to go ahead and do t equals 0. So for that one, we get r of 0 is equal to 0i minus 4j plus 0k. Okay, so 0i minus 4j plus 0k. Because x is always 0 in this particular equation, right? And then y is 0 squared minus 4, which is -4. And then z is 4 times 0, which is 0. Okay, so our second point here is going to be 0, -4, 0. So y is -4 and everything else is 0. So now we can plot this point on the y-axis, but keep in mind that we're only going out to -4. Okay, -8's way out here, but we're not going out to -8. Okay? And that -4 is actually when t equals 0. Okay, and then we need to do at least one more point, even though we can see that we're going like this. So we expect our parabola to end up here at +8. We should probably do at least one more point just to make sure that we've got the right graph. Okay, so we're going to go ahead and do t equals 2, which is going to be the very end of our graph. So when t equals 2, we get r of 2, and after we plug that in, we're going to get 2 squared is 4 minus 4 is 0. So we're going to get 0i plus 0j plus 4 times 2 is 8k. Okay, so our point here is going to be 0, 0, 8. And that's actually what we expected for a parabola, or hopefully what we expected. So 0, 0, 8 is going to be at 8 on the positive z-axis. Okay, and that's where our graph ends at t equals 2. Now, if we didn't know that if it was a parabola, we might want to plot more points. So for example, we could do t equals -1 and t equals +1. But because we know it's a parabola, I think most of us can see what this parabola is going to look like. It's going to start here at t equals -2, and then it's going to pass through -4, and then it's going to turn around so that it can pass through +8. Okay, and obviously it's not an entire parabola because it starts at -8 and it ends at +8. But we can see the shape here. Okay? And then the last thing we need to do, of course, is to make an arrow showing the direction that this shape is traveling. So since we start down here at -2, t equals -2, and we go here and then we go up there, the direction of our graph is going to be up. Okay, so we need to draw an arrow here and an arrow there. And once again, I'm not big on taking the derivative, but some people take the derivative so that they know the velocity at each of those points. That's another way of knowing that the graph is going that direction. But I feel that that's unnecessary and that plotting points just works just fine on these problems at least. Okay? So that is our third graph. And that completes this lecture. Thanks for watching.